we're going to take a look at linear and nonlinear functions. And there's a couple of things that I wanted to point out. First off, if it's linear, if it makes a straight line when we graph it, that's really nice because then we actually know what the rate of change is. We know so many different ways to get the slope already. Anytime you see them talk about the rate of change, it's just automatically the slope. And then the other thing is that we can find the equation, or we can use an equation to identify what's going on with this linear function. And that's very helpful. So it's just a lot of information that we're already familiar with. It's the nonlinear functions that when we deal with those, it's a little bit of uncharted territory, and we've not really worked with a lot of nonlinear functions. And what we need to do today is get you used to looking at the two different types of functions and go, okay, that's linear and that's nonlinear. And obviously you can tell when you look at a graph, but when you're looking at an equation or a data set that's hidden in a table, an XY table, that's when we need to have you start being able to roll up your sleeves and be able to figure out, is this linear or is it nonlinear? So let's take a look at everything else that we're looking at. And remember, anything that's not linear would be considered nonlinear. So let's cover up this little bit and look at these first three graphs. If we see a straight line, it's going to be linear. Okay, so this first one is linear. There's a reason that the word line is actually inside of the word linear. So anytime you see a straight line, it's linear. If you see anything that's not a straight line, then that's obviously nonlinear. And I throw this one in anytime that you can actually draw a straight line and it would connect all of the dots that are on there, you could consider that linear. So this would be linear like this. However, I did want to point this out. If we put in some extra dots, I could not call this a linear function because I could not draw one line and have it be straight and touch every single dot. I would have to play connect the dots, and then I would have a nonlinear line there. So how it's looking right now would be nonlinear. If I take those green dots off, suddenly we would say, yeah, that's linear. Okay, now that's the easy part. I don't think anybody's going to have much trouble with that. The next part's pretty easy too, and that's when we give you equations. So here's an equation, and in fact we know it's in the slope-intercept form. And I hope at this point that you know that the y-intercept would be positive 22 and our slope would be 5, so we'd go up 5 spots from 22 and over 1, and we'd go up 5 more and over 1, and we could connect all those points and it would be a straight line. Over here we get y equals 5x to the second power minus 6. And I'm actually going to pull up a calculator, and I'm going to put this in here and hit the graph button and let you be able to see that. Here's my graphing calculator. If I hit my y equal button, that represents this y equal part of this equation, and I can type in 5x to the second power minus 6. So 5x to the second power minus 6. And then if I just say, hey, graph it and choose how I want it to look like, I'll say the standard view. That blue line is graphing it for me. And you can tell that this is definitely not a straight line, so it's not linear, so this equation is nonlinear. And it's at this point that I'd like to take just a moment and have you look at the difference between these two equations. The plus 22 and the minus 6, that's just your y-intercept, okay? And if you don't believe me, look, this is negative 6 or minus 6. That's what's touching right here on the y-axis, so that's still your y-intercept number right there. The big difference is that this x has no exponent and this x does have an exponent. And so if you're looking for the easiest rule of, hey, how can I tell if an equation is linear or nonlinear, it's pretty simple. If you see no exponents on the x, it's linear. If you see an exponent that's on the x, it's nonlinear. So let's take a look at these two equations right here. Here's y equals x to the second power. Well, the x has an exponent on there, so I'm going to say this is nonlinear. And since I've got my calculator up, let's just go ahead and pop that in and see what it looks like. It would be x to the second power. If I hit graph, you'll see that it's going to start graphing right up like this. And for those that are trying to relate how the y-intercept touches into this, the y-intercept is 0, and so if I wanted, I could put plus 0 right here. But again, it's nonlinear. Why? Because this x value has an exponent on there. That x variable has an exponent. Let's take a look at this one. Y equals 2x plus 3 to the third power. This one is actually linear. And if you're saying, whoa, 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 I see an exponent, this exponent is not on the x variable. So that's why it's going to be just a nice straight line when we graph it. And just to prove it to you, I will type it in exactly how it is. Let's see, 2x plus 3 to the third power. And then I just need to get that 2 off of there. There we go. So y equals 2x plus 3 to the third power. And when I hit graph, you'll see that it's starting to go straight line. Well, on my y-axis on my graphing calculator, that's a positive 10, and 3 to the third power is 27. So if I say zoom and hit my 0 button, it'll actually fit it in where we can see it. That's positive 27 on the y-axis, and it's going straight through in a nice straight line. So this is definitely linear. Don't let those exponents on a number fool you. It's the exponent on the x. Now, that's the easier part of the lesson, and now we need to really roll up our sleeves and focus on this last part. How to tell if the ordered pairs or table data is linear or nonlinear, if the case might be. Here's an example where we can show that it would be linear. So let's just say we have a table. We don't know what it looks like when it's graphed. What do we do to test to see if it's linear? Well, linear lines have constant slopes. That means the slope is always the same no matter what between the points. So what we do is we literally say, okay, I'm going to take the first 2 points and I'm going to see what the slope is between them. So 26 minus 16, y minus y, right? Y minus y over x minus x, so 2 minus 0. And that equals 10 over 2, or positive 5. I'm going to draw a line right there just to kind of keep that separated. Now, what's going to happen now is I'm going to say, how about I find the slope between these 2 points? If this is linear, I will get 5 again. If I get anything other than positive 5, it's not linear. So here we go, 41 minus 26 over 5 minus 2. If you rush it, you make a horrible mistake, and you won't know for sure if you get it. If you just take your time and just cruise through there and focus, you'll be okay. 5 minus 2 is 3. 15 divided by 3 is 5. So since I got the same slope using different points, see, I used these two and circled in green for this, and we got 5. And then I used these two circled in red for this, and we got 5. We know it's linear. Here's the example of what happens when it's not linear. So let's go through and let's take these 2 points and let's see what the slope is between these. 18 minus 6 over 2 minus 0. Well, that's 12 over 2, or positive 6. Let's go through and see if we get positive 6 again. This time I'm going to use blue. So we'll use these. 18 minus 18. Well, that does not bode well for us. And negative 2 minus 2. So negative 2 minus 2. And we get 0 over negative 4. Sorry, but 0 over negative 4 is not 6. 0 divided by negative 4 is 0. And so since these two slopes are not the same, they're not constant, this is nonlinear. And that's what it is. And so now we know that we can't do any of the tricks like we can for the linear functions, the linear equations, because quite frankly, there are certain properties available in linear functions where, the slope is the same, and so that gives it a certain amount of predictability. When we're looking at these nonlinear equations, we're just saying you don't have enough of a tool set to really do a lot of extra work with this. Also, another thing to take a look at here, even though I've got this as equations, we can also just change the word equations to functions. I mean, that's not a huge deal. Um, it's pretty much the same thing. All functions have rules. Well, the rules would actually be your equation. And the last thing that I want to kind of sneak into this video real quick is, could we get an equation, a function rule for this table set? Sure. We have our slope, so just go and use our point slope format to go figure out what our function rule is, or another name for a function rule is an equation. You stick 5 in here for m, and you stick one of these points in here for the y1 and x1 and go solve for y. And that's what would happen. I'm not going to show all the steps, but basically the function rule for this function would be y equals 5x plus 16. Every input's multiplied by 5, and then add 16 to it. So here's our input of 0. 0 times 5 is 0, and 0 plus 16 is 16, so our output y is 16, and there it is on the graph. You can check it with these two inputs also, and you'd get the same outputs every time. Brief recap, because it's been about 11 minutes. Look, if you can look at the graph and tell it's not a straight line, it's nonlinear. If it is a straight line, it's linear. For the equations, if we're trying to tell it the difference from the equations, if the x has a exponent, it's nonlinear. If there's no exponent on the x, it's linear, and that's what it is, pure and simple. And then here, if we give you table data, basically go through and check all of the points that they give you, mix and match, and see if you get the same slope all the way down. If you don't get the same slope, you know it's not going to be a straight line, so it's a nonlinear function.